Hi, my name is Yoad Lewenberg, and I will talk about Spectre. I will focus more on the implementation details and a more efficient approach. The work on Spectre was done while I was a PhD student at the Hebrew University of Jerusalem with Jonathan Sampolinsky and Aviv Zohar, and now I'm working with Jonathan Sampolinsky on DAGLabs. So the motivation of Spectre and in general DAG-based protocol, as David mentioned today in the beginning, and already Chris talked about the general graph, is in the scalability of Bitcoins. The confirmation time for a transaction in Bitcoin could be within the minutes, because if we have one block every few minutes, and we want to wait more than one block, we need to wait, for example, up to 30 minutes for a transaction. If we compare it to fiat money, to Visa or PayPal, where we got a confirmation within the second, also the throughput of Bitcoin and other cryptocurrency is within only a few transactions per second that we can process, compared to a few thousand transactions per second that a fiat money system can process. So if we simply just want to scale Bitcoin or other cryptocurrency, we can just increase the block creation rate. Instead of having one block every few seconds, every few minutes, we can have one block every few seconds, but the longest chain rule does not scale very well. We will have more forks in the network. We have some delays in the communication, as Roman mentioned earlier. So we need to come with better approaches for a more fast cryptocurrency. Just to summarize this section, if we want to decrease the waiting time, we may increase the block creation rate, but it hurts the security because we will have more forks in the network. And you can see, for example, here to the left side, there is some graph. It's based on work from Decker and Wattenhofer from 2013, but the data, I believe, is still relevant. We can see how much time it takes for 25, 50, and 75% of the nodes in the network to receive a block as a function of the block size, and we can see that it takes a few seconds, up to more than a minute, just to receive a less than 1 kilobyte size of block. So we need to come with a different solution. So we proposed in a paper in 2015 to move from blockchain to block DAG. The main difference between blockchain and block DAGs, in blockchain every block only refers one predecessor, and in block DAGs we ask every block or every miner to point all the blocks that he is aware of. So we have simply just two basic rules for the miners. Is first of all, reference all previous blocks that you are aware of. It's enough just to point the leave block, the one without any child block, the one that nobody is referring them. And the second rule is we will ask the miners to publish immediately every block that they created. But this is still a proof of work block. Block DAG, the blocks are created in the same way. But block DAG is basically just a framework. On top of a block DAG, we need some protocol that we can verify now which transactions are confirmed and which one are not. For example, in this block DAG, we have two transactions. They may be conflicting transactions. In the top, we have the blue user that sent some money to the orange user, and in a different block we have the blue user that sends the same money to a different user. It may be the same account, a different account of the same user, and we need to decide which of these transactions is valid, if any. We can say that none of these transactions is valid. So on top of block DAG, we need to have some protocol that we can reach a consensus about the confirmed set of transactions. And why block DAG as I believe, is more challenging than the blockchain, I like to think about the analogy of a single lane versus multi-lane highway. If we just take a snapshot of a single lane highway and we need to decide to reach a consensus on the order of cars, it's much more easy if we see just one lane. But if you have a multi-lane highway, now everybody takes a bit different snapshot of the status of the highway and we need to reach consensus about the order, it's much more challenging. And it's challenging because not all the miners are honest. Some of them are maybe even some kind of a manipulation. And the first challenge is just to identify the attack, and then we want to punish the attacker. So I want to say, present in this slide, that even identifying the attack is not easy. So, for example, in this slide, I think it's a bit easy to see what blocks are part of an attack. And I think that you all agree that here the blocks on the bottom are part of the attack because we have a side chain of an attacker. It was a secret chain. It only references his own blocks, and it's not published, so no other nodes is referencing this side chain. But it can become more challenging. For example, in this case, this was the attack, but here, where is the attacker? Where are the blocks that belong to, they are part of the attack, that belong to the attacker? So it's a bit, become a bit more challenging. In this case, there are the blocks that are on the top. We can see it was not a secret chain. The attacker did publish his block because we see that other nodes also publishing this chain, but he only referenced his own block. And again, this is not what we ask for the miner. We ask him to reference all known block. And in the last case, we also have here an attack. In this example, this is a different kind of an attack. In this case, we have an attacker that kept secret his own blocks. He did not publish it. But he also pointed his own block. So we want a protocol that will first know to identify this kind of attack, and we also want to punish the attacker. We want to incentivize node to follow the protocol. So as I said earlier, on top of any block DAG, we want some kind of protocol that will tell us the order between blocks. For example, if we have in two blocks two conflicting transactions, it might be the case that in every block we only have one transaction, but we still need to reach a consensus which transaction is valid. And we also have some properties that we wish our consensus to follow. For example, we want the order to become robust in time. For example, if now I say that the top transaction here is valid, as time goes, I want to have more confidence that this transaction is valid. If I accepted as a merchant a transaction, I don't want after a few minutes to say, wait a minute, maybe the transaction is not valid anymore. And again, we want to punish any secret blocks, any blocks that may be part of an attack. We want them to be with high probability punished to incentivize nodes to follow the protocol. So on top of the block DAG, we came up with the Spectre protocol. Roman already presented the protocol, so I want to go the definition with a bit more details in this time. So what Spectre does is for every pair of block, we ask every block what is our opinion about the order of the block. It's not like that with the opinion of a block is really written within the block. We see the DAG and we interrupt as every block voted for a pair of blocks. For example, here we have two blocks, B and R, blue and red. We interrupt the DAG as every other block has opinion which block came first, the blue block or the red block. Every block has its own opinion. We go to election and the majority wins. If we have more blocks that believe that the red block came first, then the opinion of the DAG is that the red block came first. If the majority said that the blue block came first, then the opinion of the DAG is that the blue block came first. And after we go to election, we take the majority opinion and then we decide the order. So we have a few thumb rule on Spectre. First of all, we want to keep topology order. So if we have block Z that says there is a path in the DAG from block R to block B, and we ask block Z, which block do you believe that came first? So we said, I believe that block B came before block R, because in the DAG, we see this is the first block, this is the genesis, the time goes here to the right, or yes, to the right. So we want to keep the topological order. The second rule is that if we have a block Z that sees in his past one of the block, in this example, he sees in the past only block B, and he doesn't see block R, so he believes that block B came before block R. We want to keep advantage block that you see in his past is just to incentivize miners to publish as soon as possible their own blocks. So in the same case, for example, all the reddish block here believe that block R came before block B, and all the bluish block here believe the opposite. And the other rule is, or it's not the last rule, that if we have a block, in this example again, block Z that sees both block Z, B, and block B, and we want to figure out which block came first, so this block goes to election, it looks at his past and takes the majority of the opinion of the block in his past. So now he looks for all the block here that marked with a yellow line. He see if most of the blocks say that block R came first, he believes that block R came first, and so on. The last rule that we have, if we have a block that does not see in its past neither block B nor block R, so it takes a majority over its future, all the blocks that have a path to this block. So in this case, all the blocks that are marked with yellow, we ask their opinion about the order, and if the majority say that block R came first, this will be the opinion of what now is marked with block Z. This is also be the case in this example. We again have a block still marked with the letter Z that does not see in its past neither block B nor block R, so we will take a majority over his future. So we have a few properties on Spectre, and they are proved in the paper, so I don't want to go into the technical details, so I just say that Spectre is both safe and is also a both secure protocol, and also the order become robust on time, which means that if I see my snapshot of the DAG and I think that one transaction is confirmed, so eventually every other miner will think the same, and it's a progress. It means that if now I have confidence that one transaction is confirmed, as time goes, I likely to have gained more confidence about this order. So this was just for me the introduction about Spectre. Now I want to try to convince you that Spectre is a really nice and interesting protocol, but the naive implementation is not feasible because we have a lot of recursive computation. So let's just bear with me this simple example. So say that we have this DAG, this is the Genesis block, and we have two blocks B and R, and we want to figure out what is the opinion of this DAG about the order of the block B and R. So we have a few basic rules. For example, if you have this block Z, he only sees in the past block B, he does not see block R, so this case is easy. So he believes that block B came first, and this is why this block now marked, if you can see it, with a blue line. In the same way, also the other block, what now is marked with the letter Z, also believes that block R came first, because he only sees block R. But now we have the new block Z, he sees both block B and R, so he needs to decide which one came first. So now we have a recursive call. We look about the sub-DAGs that consist only of the past of block Z. This is the block that now you can see, and we now need to figure out what is the opinion of every block in this DAG, take the majority, and this is how we know the opinion of what used to be block R. So block Z. So we know the opinion of the blue and red block, so we can go about different block. This one only sees in future block B, so it will be marked as blue. The other two blocks only see in their future only block R, so they will be marked with red. The Genesis see in the future 3 blocks that are voting for red, 2 blocks that were voting for blue, so it takes a majority, 3/2, so he believes that block R wins the majority, and this is now, we return from the recursive call, we see 4 votes for the red, 3 votes for the blue. We can conclude that what used to be block Z will vote for the red block instead of the blue vote. So this was just one calculation for one vote, and we need to continue with the other blocks. Now we need to recalculate the opinion of the same block, because now it's a different DAG, so I don't want to take much of the time. And this block also looks at the future and take a majority, and so on and so forth. So after we're done with all the recursive computation, we can figure out what the opinion of every block and take the majority and see that the opinion of this DAG, that the red block is came before the blue block. The reason that I gave you this example is just to try to convince you that if we do Spectre naively, we have a lot of recursive call, which is not feasible. So what I did here in this example, I simulated a network of miners, and I played with the number of blocks that this network can generate every second. I started with half a block per second on average until 5 blocks on average per second. And I also played with the simulation lengths. I started with a few hundred seconds and until 50,000 seconds. After the simulation was done, I randomly picked 2 blocks in the middle of the DAG, and I performed the DAG. I executed the DAG protocol. I wanted to figure out what is the order. So, I measured the time it took me to do it. I used a not very new laptop, but it will be true for every machine. So what we're seeing here is that it's not surprising. We see that as we have more blocks per second, as the network working in higher throughput, the computation time is higher, which should not be a surprise. But what we also saw here is that if I tried in bigger and bigger DAGs, also the computation time grows with the size of the DAG, with the size of the simulation time, which is not a good output. We don't see here all the result because after 30 minutes, I just terminated the simulation because it didn't end, and I didn't have much time to do it. So obviously we cannot propose a protocol that we can say maybe in the few weeks or few months we are able to figure out to reach a consensus to run the protocol, but after 1 year, 6 months, 2 years, and so on, the complexity is too high for every machine. So obviously the naive approach of Spectre is not feasible. We must come with some different approaches. And what I want to do in the rest of the time that I have, I want to propose just to talk about 2 approaches that we use that improved significantly the running time. So first of all, we figure out that if we are doing the right computation in the right order, we can save a lot of time if we can make sure that every time that need to take into consideration the vote of a block, we have this information already ready, and we store it in the data structure. It saves us a lot of time. We don't need to do the exact same computation twice. So what we came up that if you want to figure out the order of the blue and red blocks in this example, so first we start with the red and blue blocks, and we go over from those blocks in topological order towards the leaf of the blocks, towards the newest block. In this case, we have all the information that we need ready just on time. And when we go on the other blocks that don't have in the future neither block B nor block R, in this case, we go with the reverse order. We start with the newest block until we reach the genesis in a reverse topological order. In this case, when we need to know the opinion of a block, we have this information ready. And the second, and which is more interesting but technical, the approach that we came up is to know when we stop. In some cases, we have a very strong majority, so there's no point of trying to compute what is the opinion of the other blocks because we can figure it out. If we have just one block that is so convinced that the blue block winning over the red block, we don't need to ask all of the other blocks because we can understand what they are going to see, and they are not likely to say the same. They must have the same opinion. So our second approach, which was more challenging, is to identify those cases when the majority is so strong that the opinion cannot be flipped. We are looking, when we compute in the recursive call, we know that the majority toward one block is so strong that we can terminate the recursive call and just come up with the right solution instead of just computing the opinion of all of the DAG. So we ran the same simulation with our efficient approaches. So just to remember, without of this efficient approaches, in some cases the computation time was more than 30 minutes. This is where we're terminated. In this case, every computation was less than a second. It also depends on the exact 2 blocks that we randomly picked, but we can see that on a slow machine, also for a very high throughput to 5 transactions per second, we can have 1 query for less than 1 second. We have a few queries per second. If you use a stronger machine, obviously it becomes faster, which make the Spectre protocol be feasible, and it could be implemented. So this is what I wanted to talk today, and thank you very much for listening.
Great, thank you, Yoad. We have time for questions. If anybody has a burning question they'd like to ask. Chris, right here.
Yes.
Just a quick question on the slide before. I just didn't understand what the axes on the graph were.
Okay, so here I simulated a network with, in this case it was a 30 miner, and I fixed the delay between every 2 nodes to be 2 seconds. Okay, I have more time. And I terminated the simulation after either 50, oh, you cannot see it, oh, sorry, after 50,000 seconds, after 10,000 seconds, and a few hundreds. This is the dots here. So if we have a longer simulation, it means that we have a much bigger DAG. And I also played with the number of blocks that all the nodes create on expectation per second, starting with half a block per second or 1 block every 2 seconds to 5 blocks per second. Okay. So if we have more blocks per second, we have more blocks that are not aware of each other, that created roughly at the same time, because again, the delay was fixed. Because for us, it's easier, if we have a change, the one extreme is the easier. If we have a really high delay, this is the other extreme, which is the harder for us. So obviously, when we have more blocks per second, the computation time will be higher, because we have the instance is more complicated. But if we have a bigger DAG, we don't want it to affect the computation time. We don't want to say that in the first year we can perform the protocol in less than a second, but after 10 years it's going to be 10 seconds. So it's not feasible in this case.
Yeah, okay.
Great. We have a question right at the back there.
Again, I can't remember.
Why don't you just have some asymptotics on this?
Why don't I have?
Why don't you just have some closed form asymptotics on this instead of the estimate?
Because this is not a rule, this is some kind of a heuristic that we can know, for example, in which time we can stop the computation. If you just want to, we can't have a proof that every time we can stop the termination after such and such second, because in the extreme case, one can create a case that we have to do all over the DAG. So this is just a random example to show you that it's more efficient just doing it naively.
I've got 2 questions. So one, is there a good way to concisely say the difference between Spectre and Phantom? And the previous speaker mentioned there was a security vulnerability for Phantom. So is that true, or? Okay,
so I'm not an expert on Phantom, and I was not involved on the result, so I don't want to talk on their behalf.
Were there any other questions at this point? I have what might be a fairly simple question. Sure. So if you've got like parallel mining of blocks going on,
yes.
How does double spending work? What's to stop me from trying to spend the same output twice in 2 blocks being mined in parallel?
So the idea of our protocol, the Spectre protocol, and we believe any good DAG-based protocol, that if you did not publish your block very early as soon as created, the protocol by itself should punish you. In this case, for example, if you have the 2 blocks that created roughly at the same time, not part of any kind of attack, it's fine. So but we still need to figure out which one came first in case we have a conflicting transaction. But we don't want to incentivize you to try to do double spending. So this is why we also give you good votes if someone sees you, a good vote if you see a lot of people. So we try to balance.
Okay, great, thank you.